Assalamu alaikum and welcome to the chapter review of Appendix A, that is the hidden Markov models. I, Miftah Janat Maliha, will be covering the Markov chain and the hidden Markov model. The hidden Markov model is based on argumenting the Markov chain. A Markov chain is a model that tells us something about the probabilities of sequence of random variable states, each of which can take on values from some set. These sets can be words or tags or symbols representing anything. A Markov chain makes a very strong assumption that if we want to predict the future in the sequence, all that matters is the current state. A Markov chain is represented by three components, and those are firstly Q, which is the set of n states. Secondly, a transition probability matrix A that represents the probability of moving from a state to another. And thirdly, an initially probability distribution over the states, that is pi. The first order hidden Markov model instantiates two simplifying assumptions. Firstly, the Markov assumption that says that the probability of a particular state depends only on the previous state. That means the probability of a state Qi, given that all the states from Q1 to Qi minus 1 will be equal to the probability of Qi, given that only the last state, that is the Q of I minus 1. Secondly, the output independence that says that the probability of an output observation depends only on the state that produced the observation and not on any other states or any other observation. Given the equation that probability of the state OI, that is the output observation, will depend only on the state that is produced as the observation, that is the probability of Qi. An idea have been introduced that the T-hidden Markov model should be characterized by three fundamental problems. Those are firstly, problem one, likelihood. Given that HMM lambda equal to A given B and an observation sequence O, determine the likelihood that is probability of O given lambda. Secondly, decoding. Given an observation sequence O and an HMM lambda equal to AB, discover the best hidden state sequence Q. And thirdly, the problem 3, that is learning. Given an observation sequence O and the set of states in the HMM, learn the HMM parameters A and B. That's all from me. Thank you.
Good evening and Assalamu alaikum. I'm Farhin Rahman. Today I'm going to talk about part A.3 of our book chapter Hidden Markov Model. First, we compute the likelihood of an observation sequence. Given figure A.2, what is the probability of 313? From Markov chain where surface observations are the same as hidden events, we may determine the probability of 313 by following the labeled states and multiplying the probabilities along the arcs. Hidden Markov models are complicated. We wish to calculate the likelihood of a 313 ice cream observation sequence. But we don't know the hidden state sequence. Let's start basic. If we knew the weather, we could guess how much ice cream Jason would eat. Many HMM tasks use this. We can readily compute the output likelihood of 313 for a given hidden state sequence. For example, hot, hot, cold, cold. How? First, hidden Markov models produce one observation per hidden state. Thus, hidden states and observations have the same duration. We utilize the ON2T forward algorithm instead of an exponential one. Forward is a dynamic programming approach that employs a table to hold interim values as it develops observation sequence probability. The forward algorithm computes the observation probability by summing all alternative hidden state paths that could yield the observation sequence. It does so effectively by automatically folding each path into a single forward trellis. My teammate will proceed from here. Thank you.
Hello and Assalamu alaikum. This is Alna Shubhra Trisha, and today I'll be covering the Viterbi algorithm. So let's get into the definition of the Viterbi algorithm. Well, Viterbi algorithm is a recursive optimal solution to the problem of estimating the state sequence of discrete time finite state of Markov process observed in memoryless notice. So from the concept map, we already seen that hidden Markov models are connected with the Viterbi algorithm, and hidden Markov model has been solved in Viterbi algorithm. So Viterbi algorithm is also following the hidden Markov process. Then what is the hidden Markov model? We need to find its definition too. Hidden states are which has transitional probabilities, and those hidden states have emission probabilities too, is a reference of hidden Markov model. So we can finally say that Viterbi algorithm allows to solve this hidden Markov model in an efficient way, and the steps that had been followed from this algorithm are decode, algorithm, backpointers, probability. So backpointers are the key idea of the Viterbi model because it gives the final solution. So we can see initialization, recursion, and through the termination it comes up with the final solution. So we would have some observation sets which would be provided, and we need to find the hidden sequence through the algorithm. With that being said, I would be concluding my video. Thanks for watching.
Assalamu alaikum. I am Faisal Ahmed, ID 19101535. In the hidden Markov model, there are three fundamental problems: likelihood, decoding, and learning. Learning means learning the parameters of the hidden Markov model. For example, given an observation sequence O and the set of possible states in the hidden Markov model, learning the hidden Markov model parameters A and B. The standard algorithm for HMM training is the forward-backward or Baum-Welch algorithm, a special case of expectation maximization or EM algorithm. The algorithm will let us train both the transition probabilities A and the emission probabilities B of the hidden Markov model. EM is an iterative algorithm computing a initial estimate for the probabilities, then using those estimates to compute a better estimate, and so on, iteratively improving the probabilities that it learns. The forward-backward algorithm is an inference algorithm for hidden Markov models, which computes the posterior marginals of all hidden state variable given a sequence of observations or emissions. For example, it computes all the hidden state variables, the distribution. This inference task is usually called smoothing. The algorithm makes use of principle of dynamic programming to efficiently compute the values that are required to obtain the posterior marginal distribution in two phases. The first phase goes forward in time while the second goes backward in time, hence the name forward-backward algorithm. The forward-backward algorithm starts with some initial estimation of the HMM parameters. We then iteratively run two steps. Like other cases of EM, expectation maximization algorithm, the forward-backward algorithm has two steps: the expectation step or E step and the maximization step or M step. In E step, we compute the expected state occupancy count and the expected state transition count from earlier A and B probabilities. In the M step, we recompute new A and B probabilities. Although in principle the forward-backward algorithm can do completely unsupervised learning of the A and B parameters, in practice the initial conditions are very important. For this reason, the algorithm is often given extra information. For example, for HMM based speech recognition, the HMM structure is often set by hand, and only the emission and A transition probabilities are trained from a set of observation sequences. Thank you. That's all from my side.